Lauren Keough, speaking on determining and distinguishing Mycielskian graphs. Lauren is a professor at Grand Valley State University and also has the distinction of having shared an office with me for 3 years in grad school and prepared the perfect sign many years ago, prepared the perfect sign for my expectations for this talk. So take it away, Lauren.
I am trying to remember the origination of that sign. It may have been comps or something.
It was for my comprehensive.
Yes. Thank you, Rachel. So thanks to Rachel for inviting me. It's nice to see a bunch of familiar faces. So I have not given a seminar talk. This is my first pandemic seminar talk. So it has been at least a year, and I think it has been longer than that. So bear with me if I accidentally ask you to do something and send you to breakout rooms. That's just a reflex from teaching, and we'll recover from that. So this work, though, started just pre-pandemic in the summer of 2019. So it is with WIGA, so the Women in Graph Theory and Applications workshop that happened at the IMA. You may recognize some faces. Here's Ron Graham and Fan Chung are here. I am here. You can find Rachel because she is wearing purple. There's a lot of purple in that section, but if you're ever looking for Rachel in a picture, that's a tip. And so this is a blurry picture from the website, but here's a better picture of my specific collaborators. So maybe I'll in pink. This is Kat Perry. Kat is at Soka University, which is in Southern California. This is Minnie, who's not on this project, but is in our group. This is Sally Cockburn, who's at the Hamilton College. Puck Rombach, who is at the University of Vermont. This is Debra, who is also at Hamilton College. This is me. And this is Sarah Loeb, who's at Hampton-Sydney College, and we got together to work on determining and distinguishing numbers of graphs. So before I get into that, so our project stemmed from doing determining and distinguishing, but I'm going to tell you a little bit about what a Mycielski graph is, which you may know already, but in case you have forgotten. So what you do with a Mycielski graph is you take a graph G. So here circled in pink, this is my original graph, which is a P3 and then 2 K1s. And what you do is for each vertex in the graph, you make a copy of that as a shadow vertex. And so this is the set of my shadow vertices here. And then you add a root. And so the edges are, the root is adjacent to all of the shadow vertices. And then you take for each vertex that's in your original graph, you make its neighborhood in the shadow vertices match. So because V is adjacent to this vertex and this vertex, it will be adjacent to that vertex and that vertex in the shadows. So basically you double the degree of each vertex. And so then if we look at this vertex instead, it's only got one neighbor. And so it's got that one neighbor up in the shadow vertices. And so the original point of the Mycielskian graph is that it helps you construct triangle-free graphs of arbitrarily large chromatic degree. So what essentially happens is every time you take the Mycielskian, the clique number is going to stay the same, but the chromatic number is going to go up by 1. And so if you start with K2, that's a triangle-free graph. You take the Mycielskian of that, you get the cycle, C5, which is also triangle-free and has chromatic number 3. So that's up by 1. And then if you take the Mycielskian of that, so they iterate this process. If you take the Mycielskian of the cycle, you get something called the Groch graph, which I didn't draw here, but has a pretty picture on Wikipedia if you are curious, which is also triangle free. And the chromatic number goes up by 1 again. So it's 4, and you keep doing this and you get an arbitrarily large chromatic number in a triangle free graph. So that's what the Mycielskian is. I'm going to try to convince you that it's worth considering parameters on Mycielskian graphs by just throwing a bunch of results up here. So in addition to the clique number and the chromatic number, you can talk about the domination number. And so the domination number goes up by 1, like the chromatic number does. The packing number is the largest number of vertices so that the closed neighborhoods are disjoint. And so the packing number ends up staying the same as long as there's no isolates, because when you take the Mycielskian, that will change the packing number if there are isolates. So independent domination is just choosing a dominating set that's also an independent set. The circular chromatic number, there's been a ton of work. If you just Google Mycielskian and circular chromatic number, there's a lot of papers making progress on that. The dominator coloring number, I haven't done a ton of coloring. This is maybe my first coloring project, which is a little weird, I feel like, as a discrete mathematician. So I don't know all of the ins and outs of every coloring number, but the dominator coloring number, I believe, is you want every vertex to dominate all of the vertices in one color class. And Arumugam and Baga can show that goes up by 1 or 2 when you take the Mycielskian graph. So there's lots of parameters on Mycielskian graphs. I'm going to take a brief interlude to talk about this problem from the Journal of Recreational Mathematics. So this is maybe in part because if you ever, stop paying attention to a talk, it's nice to have something to think about. But it is also related. So maybe you'll have this in the back of your head as we're going through the talk. So let's say you have a ring of n keys and they all go to different doors, and each key only opens one door, and you can't tell the keys apart just by themselves. And so when I was in college, I think I had like little key covers, like I had a pink monkey and a blue monkey, and I put them on different keys so I knew which one was to which. But let's say you're just going to use colors to identify. So what's the fewest number of colors so that you can color the handles of the keys in such a way that you can uniquely identify each key? And so this problem appeared in the Journal of Recreational Mathematics in 1979. And maybe at the end of the talk, you can give me the answer. So in addition to the colors, you can also use like the location of the keys, right, in a reference to other colors. So yeah, that's something for you to think about. All right, so there's a good chance that most of the people here know what a graph automorphism is, but if you don't, then the rest of the talk will not make much sense. So I'm going to tell you what a graph automorphism is. So you just take a bijection of the vertices and it preserves adjacencies. So X is adjacent to Y if and only if the images are also adjacent, and vice versa. So non-adjacent vertices have to be non-adjacent. So here's the path P5. If I just label it 1, 2, 3, 4, 5, notice that you can send 1 to 5, 2 to 4, switch those vertices, leave 3 alone, and that's an automorphism. That's the only non-trivial automorphism. Of course, the do nothing is always an automorphism, but you can flip the path and that would produce the same adjacencies and non-adjacencies. With the cycle, you can rotate, right? You can rotate 5 times, or you can flip over any vertex and then through the opposite vertex. So the automorphism group of the cycle is the dihedral group, which Nick and Kian know because they are in my group theory class. And so, so there are 10 isomorphisms of the cycle. And so some of the facts that we're going to end up using in our proofs is that degrees are preserved. So of course, if you send a vertex to another vertex, they better have the same degree because you have to send all the neighbors of that vertex to the neighbors of the vertex you sent to. And so, so they preserve degrees. They also preserve distances. So if 2 vertices are 2 apart, then they better be, their images also have to be 2 apart. And neighborhoods are preserved in the sense that the neighborhood of the image has to be the image of the neighborhood. So these are types of facts that we are going to use when we prove things about determining and distinguishing colorings. I should have said at the beginning of the talk that at any point that you want to interrupt me or type something in the chat and tell me that I said something wrong, just go for it. I'm ready. So yeah, so that's what a graph automorphism is, and they are fundamental to understanding what a distinguishing coloring is. So here is how distinguishing colorings were introduced to me. So the title of our subgroup at the workshop was Breaking Symmetry. And so the idea is that there are all these symmetries in the graph, but maybe we want to break them so that the only automorphism is going to be the trivial one. And what that will allow us to do is to be able to identify our vertex uniquely by its graph properties and its color. So yeah, so here's the definition of distinguishing coloring, is we're going to color the vertices in such a way that the only color preserving automorphism is the trivial one. So what color preserving means is just that red has to go to red. Oh, this is like one of those tests where I write the color in the wrong color. and then you have to read, I don't remember which one's harder, say the colors or something. So red has to go to red, blue has to go to blue, green has to go to green in any automorphism. And if you insist on this, then the only automorphism is the trivial one. And I guess I didn't write it, but this is what a distinguishing coloring is. And like we naturally do, dist G is going to be the fewest number of colors required for such a coloring of G. So we want to minimize the number of colors that we need. That minimizing the number of colors may sound familiar to you from a few slides ago, hint, hint. Here's some examples. So here is the path graph that we looked at before. We said the only automorphism was to flip it. And so, of course, this blue vertex, if it's going to move, it has to go to the red vertex because degrees have to be the same, but that's not allowed because we're considering only color preserving automorphisms. So that means those vertices are fixed. And that means because we know the automorphism group, that all of these vertices are fixed. I will say what's nice about distinguishing colorings is that you don't always need to know the automorphism group to figure out that it's a distinguishing coloring. So it's like a little bit less work, but still gives you some measure of symmetry. So in the cycle over here in C5, we end up needing 3 colors. So if you try to color with only 2 colors, like let's say I just, use my tools to make that one red, then there is an automorphism that is color preserving. So if you go the symmetry that flips over the line I just drew, then that is a color preserving automorphism and it's non-trivial, so that's bad. We don't want that. And so we're gonna make it yellow again. And again, if you color any subset of the vertices red and the rest of them blue, there will end up being an automorphism. So anyone wanna make a guess for what the distinguishing number of the cycle is? Do this with my class. If your video is on, you can show me with your fingers. That's a good guess, Ryan, that it should be 3. And it is 3 in the case of C5, but it turns out, and also when n is 3 or 4 or 5, but it turns out that once you go up to 6, the distinguishing number is only going to be 2. So I have that picture here. So if you color like 2 vertices red, skip a vertex, another vertex red, and then color the rest of them blue, you're going to end up breaking all of the symmetries. So there you can convince yourself there is no non-trivial automorphism of this graph that preserves colors with this particular coloring, and this gets larger. So this is actually part of a theme. And so the theme is that much of the work on the distinguishing numbers shows that frequently all but a finite number of graphs have distinguishing number 2 among various graph families. So we saw it for the paths and the cycle. For n at least 2, of course, P1 is 1 distinguishable. The cycles are distinguishing number 2 for n at least 6. Bogstad and Cohen showed in 2004 that the hypercubes are mostly 2 distinguishable whenever n is at least 4. Albertson and Boutin is one of my collaborators, Debra from Hamilton, showed that Knaser graphs are 2 distinguishable. Melody Chan in 2018 showed augmented cubes and powers of hypercubes are 2 distinguishable. So there's just lots and lots of 2 distinguishable graphs. And so one of the things that people do is consider the cost. So this is kind of a tangent. But if your graph is 2 distinguishable, then you can consider what's the smallest size of a color class. So what's the smallest number of vertices that I have to color red to be able to have a distinguishing coloring? So it doesn't become uninteresting just because a lot of these distinguishing numbers are 2, like you just have to consider a slightly different problem. Okay, so now comes the motivation for the problem that I want to talk about today. So Alikhani and Soltani in 2019 showed in a paper that was actually about planar and outer planar graphs that they tacked this on at the end, that if G has at least 2 vertices and is twin-free, then the distinguishing number of the Mycielskian graph is at most the distinguishing number of G plus 1. So I'm going to briefly show you kind of how this proof works. So the reason that they say, here's my Mycielskian graph, It's got some edges, right? It's also got some edges here. That if you have twins, then you can, in an automorphism, you can just switch those two twins and do nothing else, and that will be an automorphism of your graph. I'm reading this question in the chat. Okay, we'll come back to that at the end. So anyway, so if you have twins, you can switch them, and that will be an automorphism because it'll preserve adjacencies and non-adjacencies. So they actually, in their paper, they call this R-thin, which is a term, is this a term other people have heard? No, I prefer the term twin-free. I think it's more natural for what it actually means, but they say an R-thin graph. But in any case, they're kind of preventing this from happening. So they're going to insist that there are no twins so that you can't just do this switching of two vertices. And so the other problem where the +1 comes from is basically what happens with this root vertex. So where is that root vertex allowed to go? And it turns out that it is not always fixed. And so the +1 is like, let's just give that a color that we haven't used before. Because once we give it its own unique color, then it is fixed, right? Because it can only go to vertices of the same color. And so then once they have that, then they just use kind of, I'll just color a random coloring here. That purple's for you, Rachel. Then maybe this is a distinguishing coloring of your graph G, and then you copy it on the top, right? And then what you can show is that if the root is fixed, then any automorphism of the graph G is going to, any automorphism of the graph mu of G is going to restrict to an automorphism of G. And so if you have a distinguishing coloring on G, then that fixes those vertices, and then thus it fixes the vertices above. So this result is basically this +1 is coming from color the root vertex a different color, and then the distinguishing number of G is like use a distinguishing coloring on G and copy it on the shadows. But they conjecture that you can do better than this. They conjecture that for any connected graph. So you don't necessarily need this twin-free. They say of order n at least 3, and then they hedge a little bit to say except for a finite number of graphs, that you actually don't need the +1. So there's no +1 here. That there's something that maybe you can do with the root to avoid this +1.
Lauren, is there a lower bound for dist mu of G?
We are going to get to that. So it turns out, just to spoil it, that they can be arbitrarily far apart, just because I don't want you to have to wait. Yeah, so the distinguishing number of the Mycielskian and the distinguishing number of G can be arbitrarily far apart, which I think at least in part answers your question. Okay, so here is our result. So this is Debra, Sally, me, Sarah, Puck, and Kat, proved in over the past year, basically, that basically for all graphs, as long as you're not K1 or K2, that the distinguishing number either stays the same or goes down for any graph that's not K1, K2. So we don't, I mean, the n at least 3 condition is a little silly because there's only so many graphs that have 2 or fewer vertices. But also there is no finite number of exceptions. So we don't need connected. Don't need connected. And also there are no exceptions for n at least 3. So it's slightly better than the Alikhani and Soltani conjecture. And I just threw on here like what does happen with K1 and K2 to have some easy examples to think about. So for K1, the distinguishing number is 1 because of course I can just color that way. But if you're going to take the Mycielskian of that, then you get this graph that's drawn, and you better use 2 different colors here, right? Otherwise, you're allowed to switch those. So that distinguishing number does go up by 1. And then the same thing happens with K2. If you take the distinguishing number of K2, it is 2 because you have to color these 2 different colors. But we saw that the distinguishing number of the Mycielskian, which is C5, is going to be 3. Okay, so I said the problem was the root. Well, not the problem, but the like +1 was the root. So we can think about what happens with the root, and we'll get a few different cases. So if G is K2, then you get the cycle, and the cycle is vertex transitive. So of course, this W is standing for the root, right? So phi of the root in an automorphism can be any vertex that you want. Now, if G is K1M, then it turns out that the root can be one of two things, right? It can either be itself, or it can be the shadow of the center of the star. So K1M is a star, the center of that star, the high degree vertex, it can be that. And this is actually a picture of that happening. So here, this in black, the vertices in black are the K13, and then you can see the shadows of the leaf vertices in orange here, and the shadow of the center of the star here. And then here is the root. I don't know if I said root, I meant leaves. These are the shadows of the leaves. So clearly, I shouldn't say clearly, nothing's ever clear, right? There's a symmetry here, which is that you, this vertical symmetry, right? You can just flip the whole thing, and then U4 will go to W, and all the leaves will also go to their shadow vertices, and it will fix the center of the star in the original graph. And so this happens with every K1M, it's the same drawing. And so, well, I guess for M01, right? Because that was K2, which is the cycle. And so we get that there are two possibilities for that. And then if G is not K1M, so any non-star graph, then the root does have to be fixed. And that's what's going to allow us to get rid of the +1 in almost all cases. And so, yeah, so that's sort of the big breakthrough there about what to do with the root. So I was going to walk you through a little bit of what a proof looks like for this. To give you some idea, it kind of feels like I sometimes feel like it's vertex chasing or like neighborhood chasing, like you're just chasing vertices around the graph to say like, oh, well, then this has to be independent. And if that's independent, then this happens. And so here's an idea of that proof, which is that, okay, so let's say that phi of W is actually an original vertex, meaning that it goes to the bottom layer, that graph G. Then we can show that G cannot have a dominating vertex. So let's just set up some assumptions. So let's say there are n vertices in the graph, that phi of W is V. So this is the root, and this is an original vertex. And this is the degree in G of the vertex that the root gets mapped to. So automorphisms preserve degrees. So let's just consider what the degrees have to be. So n is the degree of W because the root vertex is adjacent to all of the shadow vertices, and there are n of them because the graph has n vertices. So that's got to be the same as the degree of V because W maps to V in this automorphism. So what's the degree of V? So these, I should say, these degrees are in the Mycielskian, but I didn't write the submu of G because it's just messy. So, so this, maybe this is a mu of G here. So in G, the degree of V is K. And so in the Mycielskian, the degree is 2K because you just add exactly K neighbors among the shadow vertices. So what this gets you is that K is less than n minus 1 because n is at least 3. And so V is not a dominating vertex. So we've shown one of the vertices in the graph is not a dominating vertex, but we want to show that there is no dominating vertex in this graph. So let's say that X is dominating. Here's a fact that I got hung up on when I was reading a proof that somebody had edited. This means that X is in the neighborhood of V. And so the reason for that is because X is dominating. So X is in the neighborhood of every vertex. But like, that was 5 minutes of being like, wait, what? So, you know, sometimes you've been staring at a paper for too long, and that's a moment that you know. So anyway, we can all agree, I think, that X is in the neighborhood of V because X is dominating. So this is one of these automorphism facts. So since n of W is independent, I live across the street from a fire station and a train. It keeps class like super interesting. And it inserts natural pauses in the class. So since the neighborhood of W is independent, it must be the case that the neighborhood of the image of W is also independent because we're preserving adjacencies and non-adjacencies. And so that means that the neighborhood of V has got to be independent. Well, there's at least two things in the neighborhood of V, right? So here's V and here's X. And because that comes from above where N is 2K and N is at least 3. And so the neighborhood's independent, so that means that this is not an edge. And so X is actually not dominating. And so that shows that if you're gonna map your root to an original vertex, then there can't be a dominating vertex. So that's in general how the proofs go, but this is just, this is sort of a lemma to the lemma. Right, so this is a lemma to showing eventually that the root vertex has to be fixed. So to show that the root is fixed in general, you want to show that the root is actually never mapped to an original vertex, and that proof is similar. I'll just draw you a little picture of it. So let's say that the root is mapped to an original vertex V. Then that V has a shadow U. And basically what we do is consider where phi of U goes. And you can get like either phi of U is some original vertex or it's some shadow vertex, is a shadow vertex. And in both cases, you can get a contradiction. I think in the original vertex case, you end up getting a contradiction with there being a dominating vertex. And in the shadow vertex, I think you get a contradiction with what the degree of V has to be. But it's the same idea of chasing neighborhoods and that sort of thing. And then you can show that if the root is mapped to a shadow vertex, then it's got to be the star graph. So this is great news because now we have dealt with the root vertex, and we're going to be able to, in almost all cases, just give the root a color we have already used. So they specifically in their results eliminated twins. So let's talk about twins. So this picture I drew so that the edges wouldn't be so crazy in the middle, but I think it obscures a little bit what's actually going on. And so, but then it's like you draw a Tixie picture and you're like, I'm not doing it again. So here we are. So this is in the original graph is C4 down here. You can see like, here is my C4, just drawn non-planar. And so that's C4, and you can notice that C4 has a bunch of twins, but as long as I color, let's do it, let's make it match. Like these two vertices blue, and this vertex red, and this vertex yellow, you can see that that is a distinguishing coloring of C4, and that's exactly what this coloring is over here. So I'm gonna put a distinguishing coloring on G, just like they did, and then I'm gonna put the exact same coloring on my shadow vertices again, just like Alikhani and Soltani did. It doesn't look like that now, but here's V1 and here's its shadow over here, right? And so this is the same coloring on the shadow vertices as it is here. So what happens is, so let's say we're in the non-star case. So in the non-star case, this root ends up being fixed. Oh, that looks like I'm like giving this talk an F. F's for everyone. That was actually a common phrase of one of my grad school professors. And so memories. So the root ends up being fixed. And once the root is fixed, then your levels end up being preserved. Like the shadow vertices are going to have to permute among the shadows, and the original vertices are going to have to permute among the original vertices. So the idea is that these are all distance 1 from the root. And then these are all distance 2 from the root, unless, of course, you have an isolated vertex, in which case the top thing is distance 1 from the root, and the bottom thing just has like no distance from the root, but that doesn't affect what's happening. So that means these things together mean that the levels are preserved. So once you know that, then you know that what's going to happen down on this base level is that you need an automorphism of G. And the twins, unsurprisingly, got different colors in your coloring. because if they didn't get different colors, they would have been it would have not been a distinguishing coloring. So, so that fixes G. So then, okay, the only thing that can happen up here is that you're switching twins, but the twins are different colors because you gave the same as the coloring of G. So that means that the whole graph is fixed and the only automorphism is the trivial automorphism. So I have no idea what the automorphism group of this graph is. It's actually, maybe this one's not so hard because, like, the root is fixed, and yeah, but like you don't have to use an argument about the automorphism group to be able to say this about this graph. So that was not so bad. There is a special case where the root is not fixed, and this is an example of such a coloring. And so because the graph is K1M, you know a lot about its structure. And so the only possibility for the root was to map to the shadow vertex of the center of the star graph. So just make sure you give those different colors, and you know that you need at least 2 colors anyway, because all of these vertices are twins in your original graph. So the distinguishing number for K1M and the distinguishing number for its Mycielskian turn out to be the same. They are both M. Okay. So there is a generalized Mycielskian graph, so which is sometimes called a cone over a graph, and it's very similar to the Mycielskian, just this regular Mycielskian graph. The only difference is that you just keep adding as many levels as you want. So here we have our shadow vertices, but here we have another set of shadow vertices and another set of shadow vertices, right? And the edges that you add are very much the same. So this is still the same graph we were looking at early on. It is P3 plus 2 isolated vertices. And like this vertex is adjacent to this one and this one. And so it is adjacent to that one and that one above. And so, and then the root up here only gets adjacent to the top level shadow vertices. And so there is a ... here for add as many layers as you want. And so we were like, okay, what happens with the generalized Mycielskian? And it turns out the exact same thing. So this is also a theorem from our paper, which is that if G is not K1 or K2 and has no isolated vertices, which I'll talk about in a second, then the Mycielskian, the distinguishing number of the Mycielskian also stays the same, or it goes down. And it turns out that the lemma that we talked about generalizes. So if you're K2, then your generalized Mycielskian is a cycle on 2t plus 3 vertices, and phi of W can be any vertex. And if it's a star graph, then it's got to be the top level shadow vertex, which is why I kept almost making that mistake of saying top level shadow this whole time, is because this is the generalized lemma. So it's got to be the center of the star at the top level. And if it's not K1M, then the root is still fixed. And so that result holds, except in the case that there are isolated vertices. It's been a while since I've talked this much. So I'm going to pause for a second and drink some water. Okay, so if you have isolated vertices, this is what we would say to do with our coloring, is just give a distinguishing coloring here and then just copy it on every level. But there's clearly a problem here, because if you have more than one layer, you end up with a bunch of isolated vertices. Right? How many isolated vertices you end up with is, well, if L is the number of isolates in G, and T is the number of levels, then in your Mycielskian, you're going to get TL isolates. So this is the number of isolates in mu T of G, which also is another thing that got me hung up a couple of times, which is that the first level is like level 0. So there are in fact TL of these isolated vertices. And so we can prove in that case that if you already have enough colors to just color the isolated vertices, then that's what this result is saying. Then the distinguishing number is either the same or goes down. But if you have too many isolated vertices, then you have the distinguishing number, then the distinguishing number just turns out to be the number of isolates. So this theorem is stated as no isolated vertices, but that's only because it looks nicer. You can in fact also do the isolated vertex case. Okay, so here is Ryan's question. So they are not always equal. And so it turns out that if you have, we do an example with just Kn. So I've drawn K9 here and we are gonna color it together. And so it's a group coloring activity. And so the distinguishing number of Kn is N. It's a vertex transitive graph. And if you don't, and actually, yeah, and all the vertices are like almost like twins. So you can switch any two vertices. So the distinguishing number has to be N. And so we can actually show that the distinguishing number of the Mycielskian is the ceiling of root n. So I picked 9 because it's, you know, a perfect square that's somewhat large. So what one can do is color. I'm going to color in groups of square root n. Let's pick more fun colors. Green, like so. And then in the shadow vertices, you can color like rainbow on each group of 3 vertices. So you can color like so. And then I used purple. Oops, I missed one. And then, you know, color the root whatever you want. So the idea here is that if I switch any 2 of the vertices that are in the same color class, then it turns out that I also have to switch those in the shadow level. And in the shadow level, they end up being assigned different colors. And the root is fixed because it's Kn, so the levels are preserved. And so to generalize this, you can say something about like let K be least such that K to the T plus 1 is at least log, or is at least n. So you end up with this log, and basically number your vertices in binary and then use that to make a coloring that will do exactly this. So we can get the distinguishing number of the Mycielskian all the way down to 2 if we take enough layers all the way down from n. So they are in fact not always equal, and it's like the additional layers gives you more room to break symmetry is how I think about it. Okay, so in the last 10 minutes or so, I'm going to tell you a little bit. We've also have results on the determining numbers of graphs. So determining numbers and distinguishing numbers were developed independently, but they do turn out to be related. So the difference between a determining number and a distinguishing number is that when you pick a determining set, you're not really coloring, you're just picking a subset of the vertices. You're insisting that the vertices are fixed. So in distinguishing coloring, you are allowed to permute among the colors, but for a determining set, every automorphism is uniquely determined by its action on S, because the only automorphism that fixes S is pointwise trivial. So fixes S pointwise is trivial. So the determining number of Pn is 1 because I can just color this last, I can just pick this last vertex to be in my set, and that will be a determining set. In fact, almost any one of these vertices is determining except for this middle one, because if I just picked that one, then I could do the automorphism that flips. And the determining number for the cycle is 2, and that is true all the way down to the 3 cycle. And so, yes, so we are now thinking about, Sally sometimes thinks about this as like pinning down something very squirmy, like, and how many points do you have to pin down so that nothing else can move, right? And so, yes, so there's also past work on determining numbers. So I'll talk briefly about this relationship between distinguishing and determining. So basically, if you take a determining set and you color all of the vertices in that determining set a different color, and then color all the vertices that are not in the determining set some other color, then that'll give you a distinguishing coloring, because you're giving a unique color to everything in the determining set, you are then fixing those vertices. And then that means that the only automorphism is trivial. So Boutin has done hypercubes and Knaser graphs. They get bounds on the determining number of the Knaser graph, but you can't determine exactly for every n and k. There isn't one answer for every n and k, but there is some work in 2013 that shows that determines it exactly. in a lot of cases, but the answer is different depending on what N and K are. So what can we say about determining numbers of Mycielskian graphs? So we saw in the distinguishing colorings that the twins ended up not really mattering, but it turns out they do matter when you do determining numbers. So this is the easiest to state result, that if G is twin free and has no isolated vertices, then the determining number is exactly the same. And basically the proof is that automorphisms of G in a twin, when it's twin free, exactly correspond to automorphisms of the generalized Mycielskian. So if it's not twin free, then on a layer you could switch two twins and not switch them on other layers. And so, so you basically just take a determining set of G and show it's a determining set of the Mycielskian. And if you have a determining set of the Mycielskian, you can project it down onto G and show that's a determining set for G. So we get equality for twin free and no isolated vertices, because that also messes up for the same reason that we talked about in the generalized Mycielskian. So what do we do for determining Mycielskian graphs with twins? So just looking at these top graphs first, this is K13, and this is mu of K13, and this is the 2-layer version of K13. And so there are lots of twins here. So you can see them like these vertices are all twins and these vertices are all twins. And you get a similar thing here. Wow, yeah, these are twin to each other, and these are twin to each other, and these are twin to each other. And so whenever you're going to take a determining set with graphs with twins, you have to at least take all but one of every set of twins. Because if you don't, then you're going to end up with this automorphism that just switches twins. And so here, like I have to take this and this, or two of these black vertices that are here. I have to take at least two of these vertices in my determining set. And so what we do for graphs with twins is we actually end up taking something we call the quotient graph, which is basically collapse all of the twins down so that you can see the structure without the twins. So this big orange square is just all of these vertices. And so then you can sort of see, okay, well then, assuming that I'm going to take all of these twin vertices, then what happens with the graph that remains? What's the structure of the graph that remains? And so for this, there's kind of two cases that you can consider. In one case, like I'll draw it as a little square, the quotient graph of this is P4. But if I think about taking a minimum, we'll call it a minimum twin cover, so take all but one of the mutually twinned vertices, then in this graph, that is still a determining set. And so this, just one vertex turns out to be a determining set in this graph. But in this case, then big box for all of these twins. If I take a minimum twin cover here, so all but one vertex, then here that's not a determining set, right? So then I need to add an additional vertex to get a full determining set. And so from that, you can see as a corollary that if you take this minimum twin cover, so all but one of the vertices from the twins, and then you take the quotient graph, then the determining number is going to be between the size of the minimum twin cover, and this should have a plus size of t there. And so, yeah, so you get these bounds for twins, but actually in the end, we can do better than that. So we can show that if G is a graph with twins and no isolated vertices, and T is a minimum twin cover, then it is exactly take the T times the size of T plus the determining number of G. And that will give you a determining set of the Mycielskian. So I just want to end with saying a little bit about open problems. So one of the things that we didn't consider at all is the de-distinguishing edge coloring. So it's basically the same thing. You just color the edges and don't want any automorphism. That preserves the color classes to be to be non-trivial. And then the distinguishing index of G is the smallest D, such that you have a distinguishing edge coloring, and like we do with the chromatic number, that's dist prime. And so in the same paper by Alikhani and Soltani, they do a similar thing where they show the edge distinguishing number is at most the edge distinguishing number plus 1. And so you could ask, they do conjecture that it's less than or equal with no plus 1 in general. What is the distinguishing number in terms of, what is the edge distinguishing number in terms of the edge distinguishing number of G? Maybe you have to add some other parameters like a minimum twin cover. And then when does the distinguishing number, like for which T, like we did with Kn, can you add enough layers to get the edge distinguishing number down to 2? And that is my whole talk. And I forgot to make a thank you slide. So thanks all for listening. Any questions?
Maybe we can send the speaker.
Thank you, Ryan.
Could you go up back to your last slide?
This one?
Uh-huh. So would it be natural then to have a parameter on that last bullet point? Yeah. So that would be an invariant in and of itself. How many layers is sufficient to bring that number down to 2?
Mm-hmm. I will say, I believe this is like wide open. Like we have not thought about edge distinguishing at all. And so.
Yeah, I wouldn't think these sort of, sort of Mycielski extensions, multiple Mycielski extensions I haven't seen before. So.
Oh, okay.
Might not be terribly well.
Yeah, I think they were used, to show like arbitrarily large chromatic number with like a certain odd girth or something. I think adding the more layers does something with that. But yeah, they are not as popular as the regular Mycielskian, I would say.
And you can't necessarily get it down to 1 by doing this, right? 1, of course.
No, because there should always be a symmetry. I mean, if there's a symmetry in your original graph, there should always be a symmetry in the Mycielskian.
Yeah, you're right.
Yeah, so the only graphs that are 1 distinguishable are also asymmetric. So.
Sure.
So the question in the chat about the key problem is with ridges on one side and flat on the other, or like a typical car key with ridges on both sides. Yeah, so I think they were assuming all the keys were identical and probably also ridges on both sides so that you can't like alternate them in some way. Yeah, and use that. Like just the arrangement and the colors are what you're supposed to use to distinguish. But that's
I assumed so for sure.
Yeah, I mean, that's what we do, right? So that's another new problem. Now C5 is 2 distinguishable in some way in this.
Yeah.
You can change, if the normal keys, you can change the orientation of the keys to the coloring unless you have the same number of colors in each color class, right? For 2, and that will do the trick to distinguish the keys. I don't have to waste colors. I was doing that when I was a kid.
Oh yeah.
My kitchen that I had done.
Where did you see this problem? And yeah, no, it's probably, I think I said it was in the 1960s, so probably before your time.
Oh no, when I was at the Rainy Institute, we got one of those really old-fashioned keys, the long circular one with the, yeah.
That seems like it's probably easy to pick the lock.
Yeah. The wood was rotten enough that the lock really was far more powerful than the door.
Yeah. Did people figure out the key problem? It's just the site. It's just distinguishing the cycle. So
2 or 3.
Yeah, it's 2 or 3. As long as you have at least 6 keys, it's 2. Which to me would be counterintuitive. Like if you told me it was fewer colors with more keys, I would have told you were wrong.
Looks like there are no questions. We should thank the speaker again.
Thank you. Thanks for inviting me. I'm glad you enjoyed the talk, Zach. And yeah, it's great to be back in seminar land. And it's great that we can do this over Zoom now, right? And that, I mean, as much as I would love to travel to Iowa, it is kind of a long drive, so.
Do you have problems with those sirens at night?
No, so it turns out you quickly learn to sleep through